Hi, this is Keshav of CSA Data Science. Today our topic was Synclink, high-speed DRAM for the future. And let us start from the introduction. In 1997, it was becoming apparent that computer systems would need to communicate at data rates beyond the capabilities than the current approaches. To take on this challenge, the IEEE Future Bus Group formed a new group dedicated to building a fast, coherent interface scalable from the smallest computer to the largest mainframe. The IEEE officially established the SCI Scalable Coherent Interface Working Group, referred as IEEE P1596, in 1988. Today, the SCI is EEE Standard 1596. It has several derivatives that enhance its operation and meet conditional needs such as real-time operations, a differential voltage specification, IEEE 1596.5, a point-to-point memory interface, IEEE 1596.4, and Synclink IEEE P1596.7. Synclink is a new high-speed memory interface that combines synchronous dynamic RAM (SDRAM) developed in the late 1980s and the IEEE's Relink interface developed in 1990. Synclink uses the earlier interface packet protocol as a base but eliminates its point-to-point link to the reduced latency, and new interface uses SDRAM's internal pipelining of the control for efficient bus utilization. It allows access in the lowest latency possible for the high bandwidth. Future plans include data rates of 800 megabits per second in 1998 to double in early 2000s. This rate will allow systems to operate full capability even when running 3D graphics. Synclink development. Ramlink's physical layout was virtually the same as Sky's. Not until SDRAM was announced did we begin to look seriously at latency. We quickly saw that the 64 devices in a single link, latencies would become intolerable. For instance, with the COM CMOS technology, the best case data speed through a device appeared in to be about 6 ns. With 64 devices in the ringlet, there would be a 384 ms latency plus non-latencies incurred by the DRAMs. For the syncing, we first proposed simply to bus the 10-bit wide RAM link path to all DRAMs, allowing all devices to get the information at the same time. This bus carried a packet containing the node or DRAM identifier, the data addresses, the operation to be performed, and the data to or from the DRAM. This was the logical plan, but it turned out costly in overall operation, especially for the main memory. Space limitations prevent discussion of the assumptions about the main memory access. Tying up a single bus for all operations resulted in a usable bandwidth of about 20% of the peak. Next, we looked at allocating control addresses and write operations to separate bus from the read bus. This allowed us to use unidirectional buses, making the buses robust and improving usable bandwidth to nearly 60% of the peak. Then, using SDRAM as an example, we simulated a unidirectional control and address bus. We added a separate bidirectional data bus. This gave us the best overall operation. We now have achieved a usable bandwidth of 80% of the peak hour shows of Synclink packet structure. The device addresses 7-bit slave is in the packet's first 10-bit word, followed by the 3-bit command. Next, a 5-bit subcommand is available, followed by the 7 bits of the data addresses. Synclink's latency is one clock cycle over that of SDRAM because the first address is not available until the packet's second 10-bit word. Within a 400 MHz clock, this is additional 2.5 millisecond. With the 800 MHz clock, 1.25 millisecond. In overall scheme, the additional cycle accounts for the 2.1 of the total latency of the first access. Encoding the addresses in the packet greatly simplifies pipelining to the same or another device. And you can now see the picture of Synclink packet. See the flags are 1000, strobe are 10101, slave it subcommand and command address 0, address 1, address 2. And once look at the picture or figure for 5 to 10 seconds. The basic DRAM architecture has not changed for years. It includes the bit lines and the word lines, rows and columns, sense amplifiers, and the capacitors that need recharging to keep the associated transistors on or off. The basic physics prevents the internal DRAM from the beginning as a fast straight logic circuits. Therefore, all high-speed DRAMs need to innovative techniques to achieve high-speed input-output. Basic timings typical of today's DRAM with external I/O include row activation, which takes between the 30 and 40 Hz. In addition, column access takes from the 13 to 20 US. Getting into the device takes 3 to 4 microseconds and getting out takes to 3 to 4 nanoseconds. Thus, getting information to the outside world from the new row addresses, assuming row is ready, requires 49 to 68 US per microsecond. If we are in a row, we can get data out in 19 to 26 nanosecond. This is a best case and one we will use the demonstration. Let's say we can get the new data to the outside every 20 nanoseconds. This means that for a 16-bit wide part operating at 800 megabits per pin, we need data available for the output every 1.5 nanosecond. Hmm. This data rate would require a 256-bit wide internal bus, and the user would have to access the 16 times the external bus width in the sync link is 16 bits. The Synclink DRAM could even be used with the data input-output in parallel to give a 32-bit wide path at a 3.2 gigabytes data rate. Synclink's future. Keeping a DRAM the most inexpensive memory still a high priority. SDRAM would satisfy the needs of the systems with large banks of memory for a long time to come. Synclink's real advantage is that the granularity and the speed will continue to evolve with the processor demands. HDRAM, of course, can use the same input-output technology as Synclink. Currently, HDRAM needs 11 to 15 address pins, one or more bank select pins, and 4 or 5 control pins. Synclink has addresses, bank, control, and other functions on a single 10-bit wide control bus. Synclink gives consumers and manufacturers the speed to move ahead in 3D graphics and system processing power. If your devices and pins are limited, Synclink will be the choice for the future. If your large system memories and are not as concerned about the controller or device pin count, HDRAM would be fill the bill. But even in this situation, Synclink can keep volumes high for all memory components. Thank you.